Last time we left off with a discussion on round-off errors, and we said that round-off errors occur due to the inability of a computer to store all significant digits in a number. Computer memory can store a finite number of bits, and those bits in turn store the individual digital representations of a number. And thus, the more bits you have, the more significant digits you can store from a number. However, this is not the case in real life. We have limited precision on computers: 16, 32, 64, 128-bit, etc. And the example we did last time was to use Python to sum the number 10 to the minus 5 100,000 times. The exact value of the summation should be equal to 1 exactly. And what we did was do the summation with 16, 32, 64, and 128-bit representations of the number 10 to the minus 5. Now we know that there's round off in the representation, in the 16-bit, 32-bit, etc. representation of that number. And summing this number over a very large quantities, so 100,000 times, returned an error of 10 to the minus 1%. For the 16-bit calculation. For 32 bits was 10 to the minus 6, and smaller. Now, this may not be a large error, but it could cause a significant issue, as we will see in the next example. So round-off issues are actually a real problem, and here's one great example, a sad example for that matter, about a real situation that happened in the 90s. And if you are not familiar with the Patriot air and missile defense system, it is a surface-to-air missile defense system developed by the U.S. military to ward off any incoming missiles or intercontinental ballistic missiles. And the way it works, there's this radar shown in this diagram here that scans the sky at a certain interval. It so happens that it scans it at 0.1 second intervals. So there's an internal clock, and the radar is scanning, and then it detects an object in the sky, and then it takes another measurement. And the difference in time between those two radar pulses, it estimates the location and speed of the object, and it has some internal algorithm to detect whether this is a missile or a bird flying or something else. And there's a range if the missile, if the object is within a certain range, say 100 meters or 200 meters. Then it estimates that this is a missile, and then it deploys the battery. It sends a signal to a battery of rockets and to destroy this rocket. So this is a real picture of the Patriot missile battery. During the Gulf War in 1991, the U.S. military was at war with Iraq, and they had a base in Dhahran in Saudi Arabia. And an Iraqi Scud missile hit the barracks in Dhahran. It killed over 28 soldiers, and hundreds of soldiers were injured. It was a major disaster. And however, there was a Patriot missile defense system set up, and the Patriot system did not engage. A government investigation was set up, and it revealed that the lack of interception, the system failed to intercept because of a software error in the system's handling of timestamps. So again, like I explained earlier, the radar sends a pulse every 0.1 seconds, and it turns out that the battery was running for 100 hours, and the internal clock stored the secondary pulse in a 24-bit register rather than a 48-bit register. So the first pulse was stored in a 48-bit, the second pulse was stored in a 24-bit, and there was an error caused when the two radar pulses, the subtraction in time was taken. There was an error caused, and given that the battery was running for 100 hours, think about the for loop that we did earlier. That error accumulated over time. So the internal clock caused this error because it was running for 100 hours. Now the time the internal clock drifted by 1/3 of a second for the secondary pulse. Now you may think that that's not a big deal, but 1/3 of a second multiplied by a missile traveling at Mach 5, or about 3,700 miles per hour, that's about 1,700 meters per second. That causes the estimate of the missile to be about 600 meters, and then the battery said, "Hey, this object is far away. It's not within range, so we're gonna assume that it's not a missile." And then, lo and behold, the missile hit the barracks and caused the tragedy. There are many other disasters due to round-off errors. The Patriot missile that we just discussed, the Ariane 5 rocket, that's the French aerospace standard rocket. The software converted a 64-bit float to 12-bit integer of the sideways velocity, and then 5 seconds into the launch, the missile just turned sideways and got destroyed. You can see the video of this rocket on YouTube, actually, of this disaster. The Vancouver Stock Exchange, so just like the S&P 500 or the Dow Jones Index, the Vancouver Stock Exchange also tracks the stock market in Canada. And the representation of the index, they chopped the stock index to 3 decimal points, producing a loss of 500 points in the index, whereas in reality, the stock market had grown by 100 points. And you can see more about these round-off errors at this website for the full scoop. Now, should you worry? Not really. I mean, of course, you don't want to be the person who is causing this lack of interpretation of numbers. So, going back to the Scott situation, if both numbers were at 24 bits, there wouldn't have been this much of an issue, right? Because the error would have canceled out, right? Because then we're taking just a time difference. Same thing with the Ariane rocket. If both numbers were of the same representation, then the errors would have canceled out. So you don't want to be the person who randomly uses floats. So be very explicit in what your number representation is. And besides, most engineering and mathematical systems will cancel out the error or wash it away due to the dynamics of the problem. But just be careful. Try to understand the numbers that you are dealing with if you're writing code, whether these numbers are integers, floats, or not, and kind of what type of floats are they. Very high precision floats, 256-bit floats. Maybe the system you're dealing with requires extremely high precision, so don't make the assumption that you're only dealing with 32-bit or 64-bit floats. But don't just blindly trust numbers just because the computer returned them. Okay, always be inquisitive about the numbers. The other type of error that we will talk about, actually we had already talked about, is truncation error. And that's defined as the result of truncating an exact mathematical expression for the purposes of computer or numerical implementation. And what would be a great example of truncation error? We just talked about it in the last lecture. The Taylor series are a great example of a truncated expression. The exact mathematical expression, for example, for the exponential function has a summation of an infinite number of terms. Yet, for the purposes of a numerical implementation, we only pick a few terms, and the error that is committed there is truncation error. We measured that truncation error by doing the relative approximate error. Correct. So that was a measurement of the change in the truncation error. The more terms we added, the truncation error was reduced relatively. And so that's an example of truncation error. Now, be careful. In some computer science circles, truncation error refers to chopping a number, or other words, refers to round-off error. I think that's technically wrong. Truncation error is strictly reserved to truncating a mathematical expression due to numerical implementation needs. Chopping a number or rounding it is what happens when we represent a number on a computer. The last error that we will talk about, and that can be a little bit vague to you, is called iteration error, and it's defined as the difference between the true solution and a current iteration and approximation. And this is strictly encountered in iterative methods, which we will discuss in the next lecture. But the idea is simple, and that is, in many numerical methods, we have one recipe one equation or one formula that we will keep using over and over and over again to improve on a guess, to find the solution. Now, depending on your initial guess and where you are and the formula that you are using, every time you reuse that formula, there is an error between the true solution and the value returned by that iteration. Eventually, yes, you will converge to a solution, but the error committed in taking an iteration, that error between the iteration and the exact solution, that's called iteration error. So let me give you an example. Say you have a dictionary that has 500 pages in it, and I ask you what page is the word muse on, and give you a hint that M is kind of halfway in the alphabet, is the 13th letter in the alphabet out of 26 letters. One way to do this is say, hey, I'm going to start my guess in the middle of the dictionary. I'm just going to open it in half at page 250, and then I'm going to see what letter I'm at. Should I take the second half and then cut it in half, or take the previous half and cut it in half again, and so on and so forth. Now that just choosing the middle page causes an error between where you started your guess and the true solution of where the letter muse is. However, there could be another initial guess. You might say that the words are loaded to the front of the alphabet, so you may cut or to the second half of the alphabet. So you may start your initial guess at page 350 and then cut in 1/3 or 2/3. Now, depending that recipe of cutting and moving forward, where you choose to essentially make your next guess, that has an impact on the error. So the difference between the page you're at and the page where muse is, for example, in this case. And obviously the initial guess matters as well, and the recipe that you will use to refine your initial guess. We will talk about iterative methods once we hit iterative solvers in the next set of lectures. This lecture, this slide finishes off with error analysis, and your next homework will be assigned today, and it is about error analysis. One of the problems has to do with the Scud missile that we discussed earlier and round-off errors.